All right. So today, transforming quadratic, or basically quadratic transformations. I don't know why I wrote transforming quadratic, but really go with it. First, so here we're going to graph y equals x squared and y equals negative x squared. So when we're graphing, remember we talked about graphing the vertex? And if we're y equals x squared, that means our vertex is at 0, 0, right? And so in our axis of symmetry is at x equals 0. So we have Bless me. Oh my goodness. Oh, okay. All right. So we talked about once you have plotted your vertex and your axis of symmetry, you're going to choose points and reflect them, right? So if I was to choose 1 and plug 1 into y equals x squared, I'm going to get 1 squared. And what is 1 squared? 1. If I plug in 2, I'm going to get what? 2 squared is 4. If I plug in 3, I'm going to get 1, 2, 3, 4, 5, 6, 7, 8, 9. Agreed? And so we reflect across this axis. And I did my best. So this right here, this is our parent function. This is y equals x squared. This is where it all begins and starts from, our parent function. Okay, agreed? Now, if I have negative x squared, so when I have negative x squared, again, it's going to start at the origin. My axis of symmetry is still at x equals 0. And when I plug in the values this time, it's going to be a little different. If I have y equals negative 1 squared, that's going to equal negative 1, right? If I have y equals negative 2 squared, it's going to equal negative 4. Agreed? If I have y equals negative 3 squared, it's going to equal negative 9. So my points here are at negative 1, 1, 2, 3, 4, negative 4, 5, 6, 7, 8, 9, and negative 9. I'm going to reflect across the axis of symmetry. Uh-oh, I went too far out. Give yourself some credit. All right. Now I'm going to do my very best to connect all the dots. And bam. So what happened to my graph when the negative was placed in front? It caused it to concave down, right? So that's a reflection over what axis? Over the x-axis. So if I put a negative in front of the function, it's going to cause it to do what? If my a is negative, it's going to cause it to reflect over the x-axis. Cool? All right, next one. Now we have y equals x squared, y equals 2x squared, and y equals 1/2 x squared. So we're going to regraph our parent function. Good morning. So My cursor had disappeared. So regraphing the parent function. Pretend this is the best quadratic you've ever seen. So there's my parent function. And it wants me to graph y equals x squared. So if I was to graph y equals x squared, that means I'm plugging in y equals 2 times 1 squared. Y equals 2 times 2 squared. Does that make sense? And this gives me 2, and this gives me 8. So now at 1, I'm going up to 2. And now at 2, I'm going up to 8. So 4, 5, 6, 7, 8. Reflect the point. And connect them. What happened by multiplying by 2? It made it thinner, right? We call this a vertical stretch. Okay? It vertically stretched. It's think about, you're like, I'm going to go and I'm going to work at the gym 2 times harder. What's going to happen if they go work at the gym 2 times harder? They stretch, right? All right. Now let's think about this one. If we have 1 equals 1/2 x squared. So if I have y equals 1/2 times 1 squared and y equals 1/2 times 2 squared, I'm still at the origin. Half of 1 is what? Half, right? 0.5. And half of 4 equals 2. Agreed? So on this one, here, I'm now at a half. So instead of being at 1, I'm at a little bit of a change right there. Right? Uh-oh, sorry. The pen went away. At a half, and at 2. So what happened, pretend that these are, again, the best lines you've ever seen. So what happened with y equals 1/2 x squared compared to the red? In essence, yeah. But in this case, we call it a vertical compression. A vertical squish. So we call it a vertical compression. It got wider, right? So think about it. If you decide to cut your workout time in half, what's the chance you'll possibly get wide again, right? At least that's my story. All right. How do we feel about analyzing stretching and compressing? All right. Next. So we have y equals x squared, and we have y equals x squared plus 4, and y equals x squared minus 5. So we graph our parent function. Here's our parent function drawn to the best of my ability. And now we're going to do the first one. and it says y equals x squared plus 4. So if we have, we're going to do 1 and 2, right? So if we have y equals 1 squared plus 4, y equals, bless you, 2 squared plus 4. What's 1 squared plus 4? 5. What's 2 squared plus 4? 8. So at 1, I'm going to go up to 5, and at 2, I'm going to go up to 8. 1 up to 5, 1, 2, 3, 4, 5. 2, I'm going to go up to 8. 1, 4, 5, 6, 7, 8. And I also have to do y equals 0 squared plus 4. Because it's no longer just a coefficient in x squared. I have to account for that. And this gives me 4. So at 0, I have to go up to 4. 1, 2, 3, 4. I reflect. And now I'm here. So what happened when I added 4 to the graph? It translated up, right? So it's a vertical shift up. So when I add 4 onto the parent function, it's a vertical shift up. So what do you think is going to happen with the 5? It's going to vertically shift the parent function down, right? So if I take each point of the parent function and just shift it down 5, that's where I'll be, right? So I have 1, 2, 3, 4, 5 down. From here, 1, 2, 3, 4, 5. From here, 1, 2, 3, 4, 5. And I reflect. And here's my vertical shift down. So when I subtract 5, it's a vertical shift down. How do we fill out vertical shifts? Easy peasy. All right. 4. Now we are inside with x. So again, each graph we start with our parent function. Here's my y equals x squared. The first thing I'm going to do is y equals x plus 3 squared. So what this is saying is that I'm finding y for y equals 0 plus 3 squared, y equals 1 plus 3 squared, and y equals 2 plus 3 squared. And what happens? Well, 0 plus 3 squared gives me 9. 1 plus 3 squared gives me 16. 2 plus 3 squared is going to give me 9. Okay, and so when I plug these values in, so if I go to 0, I'm now at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Hold on. Okay, so can I graph 16 and 25? No, they're too large. So I need to choose other numbers to test out. So what if I did -1? Could I try -1? Y equals -1 plus 3 squared. That gives me -1 plus 3 is 2. 2 squared is 4. Can I graph -1, 4? Yeah. 1, 2, 3, 4. There we go. I can also do the same thing for 2. So if I plug in y equals -2 plus 3 squared, I get 1 squared, and 1 squared equals 1. So at -2, I'm at 1. So this looks like it's one side of the parabola, right? So I still need my vertex. So what if I plug in -3? Y equals -3 plus 3 squared. What do I get? 0, right? So at -3, it's at 0. So it looks like this is where my axis of symmetry is now. My axis of symmetry is now at y equals negative, and x equals -3. Didn't mean to say y. And so I can reflect these points 1, 2, 3, 1, 2, 3. 1, 2, 1, 2, and 1. And what happened to the function when I plus 3 to the x? It's called a horizontal shift. Good job. Horizontal shift to the left. So what do you think is going to happen with the -4? If it says -4, so on the x -4 squared, if plus 3 causes to go to the left, what is the 4 going to cause us to do? Exactly. So that means so at this point, I don't have to do any math. I just have to take the values of the parent function and shift them all to the right. So I'm taking this point and going to the right 4. So 1, 2, 3, 4. I'm taking this point and going to the right 4. 1, 2, 3, 4. I'm taking this point. 1, 2, 3, 4. My axis of symmetry has moved. It's now at x equals 4. And I can reflect those points. And there's my shift. So when it looks like -4, it's a horizontal shift right. So now, if you understand what they mean, do you have to do the math every single time? No, you could just take the parent function and shift it how it should be. Does that make sense? Okay, so summary. If we have the equation for quadratic in translation form is our vertex form, right? And so from here, K is what we call our vertical shift. If it says plus K, it shifts up. If it says minus K, it shifts down. H is our horizontal shift. If it says X minus H, that shifts to the right. If it says X plus H, that's going to shift to the left. A is our stretch or shrink factor, aka compress. You can either use the word shrink or compress. If X is greater than 1, then it's a stretch. If A is between 0 and 1, it's a shrink. And if A is negative, then it is a reflection across the x-axis. So that's the summary of all of that. So let's see if we can use this information. So let's see if we can describe what has taken place here. When you're describing, you want to pay attention to you want to first identify all your variables, your A, your H, and your K. What is the value of A for this problem? -1. What is the value of H for this problem? It's -2, exactly. It's a -2. And what is the value of K for this problem? -1. Okay? Because A is -1, that tells us that this is a reflection across x-axis. Okay? Because it says +2, but we know it's -2, that lets us know that this is a horizontal shift left. 2. And our K equals a -1, that lets us know that this is a vertical shift down 1. How do you feel about analyzing the transformation? Good, bad, okay? Are you ready to try another one? Oh, perfect. So on the second one, we're going to identify our A, our H, and our K. What is the A here? 1/2. What is the H? 1. And what is the K? 0. Perfect. So A equals 1/2. That means I have a vertical shrink or compression, whichever one you want, by 1/2. H equals 1. That means I horizontally, if you're going right. So I'm going to horizontally shift right 1. And if K equals 0, that means no vertical shift, right? How do you feel? All right. A equals, H equals, K equals. So for this problem, our A equals 2, our H equals 0, and our K equals 1. What does the A mean? A is greater than 1. So that means, perfect, vertical stretch. The vertical stretch by 2. There is no change here. And K equals 1 means what? Perfect. Feeling good? All right, let's look at our last one here. So the A here equals -3. The H here equals 4. And the K here equals 2. What is the transformation? The negative is its own thing. What does the negative mean? It's a reflection. So we reflect over x-axis. And the 3 itself tells us that it's a vertical stretch. Vertical stretch by 3. Okay? The h equals 4 tells us we're going what? Perfect. Shift right 4. And the k equals 2 tells us up 2. Perfect. Okay? How do you feel about analyzing transformations from the equation? Easy breezy? All right. Now let's go backwards. So now I'm going to tell you in words, and you're going to create the equation. So we have shift left 4 units and up 1 unit. Which 2 variables am I describing? The h and the k. So we know our h equals, if I'm going left 4, what? Perfect. And if I'm going up 1, our k equals 1. So my equation, remember, write it in y equals a x minus h squared plus k format. And if there is no a, then a automatically is 1, right? Casper the friendly 1. So we have y equals, a is 1. A negative times a negative is a positive. And then plus 1. How do we feel? Going backwards. Ready to try another one? Okay, so we want to stretch by a factor of 5, shift right 6 units, and up 2 units. So we have our a equals 5, our h equals 6, and our k equals 2. Plug it in. So y equals a, which is 5, x minus h, which is 6, squared plus k, which is 2. So you read and identify and plug in. Read, identify, and plug in. Let's get one more in. The bell's going to ring on us. All right, we want to reflect across the x-axis and shift down 5 units. So we have a equals reflecting, lets us know it's going to be a negative 1. There's no left and right, right? So h equals 0. And we're going down, so that's negative 5. Going to plug everything in. Y equals negative 1, x minus 0 squared minus 5. Clean it up, and we get negative x squared minus 5. All right.